I think they're here now. Yep, yeah. So we're ready for you whenever you're ready to start. I think the people at Teams have now joined.
Okay. Hi, thank you very much for the introduction. My name is Takuji, and I'm from the University of Tokyo. Uh, I work in front of such distinguished professors, postdocs, and promising students, maybe here. Today I'll be sharing my recent work titled Shift in Neural Tuning Systematically Alters Sensory Motor Learning Ability. Okay, please feel free to stop me at any point during the talk if you have any question. First, let me briefly introduce studies that I have recently published as preprints. In one of my recent studies titled Distinct Optimization of Motor Control Learning, self-paced motor learning achieves different motor patterns from overtrained. We explored whether the same movement pattern appears in different contexts when aiming for a movement goal versus executing learned action after motor run. Using self-paced movements in an average movement task, as we varied target distances 7, 10, 30 centimeters, we analyzed how movement patterns changed. We found that both movement speed measured by peak magnitude and movement time measured by the width increased with longer distances. In contrast, when we fixed the target distances at 10 centimeters, but introduced perturbations that either lengthened or shortened the cursor's endpoint location by 3 centimeters to induce motor running in the longitudinal direction, a different pattern emerged. While movement speed, the peak adjusted, the movement time, the width remained constant. This suggests that different movement patterns emerged in motor control and motor running. Since these patterns are thought to arise from an optimization process in the brain, so our findings suggest that motor control and motor running may be driven by distinct optimization mechanisms. And in this study titled Metabolic Mode, we found that metabolic mode, here I explain later, predicts long-term motor memory. So during motor learning, the brain needs to alter neural activity or induce plastic changes in its circuit with the support of energy production. Although the brain makes up just 2% of our body weight, the brain consumes 20% of our energy, and notably, it relies entirely on glucose for metabolism. So taking it into account, we aimed to predict motor learning outcomes by an estimate of whether the body was primarily metabolizing fat or carbohydrates using breathing as an indicator. We measured respiratory exchange ratio, the ratio of oxygen consumption to carbon dioxide production, to determine the balance between fat and carbohydrate metabolism. Interestingly, we discovered a positive correlation between RER during learning and motor memory retention in the next day. This suggests that participants in a glucose-dominant metabolism retained more of what they had learned. And additionally, those in the WG group who consumed glucose before the task to enhance carbohydrate metabolism retained 20% more memory than the WA group who faced it prior to the task. So these findings suggest that breathing can serve as a predictor of memory retention, and the glucose intake can improve the retention of motor learning. And finally, the third study is the one I'll be focusing on today. I'll also introduce the previous research that connected to this work. Okay, so this study was inspired by a question from my PhD supervisor, Professor Daichi Nozaki. I clearly remember the moment it came up during a casual conversation at the year-end party. And as we enjoyed drinking, eating, and randomly chatting, including our researches, Daichi happened to ask me, why and how can people correct an error? I had been conducting model learning research in an arm-reaching movement task under his supervision, and his question was directly related to my works. Many of you are familiar with arm-reaching movement tasks, but for clarity, I'll briefly explain model learning in this context. In our experiments, we measured hand movements using either a robotic manipulum or a tablet device, reflecting those movements onto a cursor displayed on the screen. In this task, participants are introduced to a perturbation where the cursor position is misaligned with the actual hand movement. In our case, we use angular errors, a technique known as visual motor rotation. When faced with this type of error, participants adapt by adjusting their movement in the opposite direction to compensate this error. So this method is widely used in our field, and we applied it in our own project. So in response to Daichi's question, I hesitantly answered, it is easy because people move leftward when a rightward error is given, and vice versa. However, there was an important underlying meaning behind this question and answer. Considering that we reach for a cup and accidentally move too far to the right, we can easily correct the error by adjusting the left on the next attempt. This is a simple example of error-based model learning. But what about babies? Imagine a baby reaching for a toy and unintentionally moving to the right. The situation is almost identical, but if the baby's motor learning ability aren't fully developed yet, the next movement might not correct the error. Instead, it could turn into exploratory behavior. So our ability to control our arms isn't something we are born with. It's something we acquire through learning, experience, and development. In the same way, our capacity for effective error correction must be something we develop over time. That is, it's not innate. So this process is often referred to as learning to learn or meta-learning. Many studies have investigated human model learning. Some try to find how model learning changes behavior. Some try to discover the neural mechanisms of learning and how neural representations are changed. And others develop improved computational models for model learning. In general, these studies aim to advance our understanding of how model learning affects our action. A relatively smaller number of studies has investigated another feature of model learning, how model learning can change the ability to learn in the future. So we know very little about it and its neural underpinnings. So my hypothesis is that motor learning ability changed along with motor control ability as babies develop both abilities simultaneously. The motor control ability can be defined as visual motor mapping. If a target positioned in front of you, you move your hand straight toward it. And if we use the y-axis for the movement direction and the x-axis for the target direction, we can plot this central point. We can accurately move our hands toward target position, various locations. So in this diagram, we can plot these points. These points will lie along the line y equals x. So this relationship between the visual target and movement execution is referred to as visual motor mapping, which can be interpreted as motor control ability. And according to my hypothesis, this motor control ability is related to motor learning ability or learning rate. To test this hypothesis, we examined how changing the shape of visual motor mapping would affect the subsequent motor learning rate. Experimentally, we distorted this visual motor mapping as if we pinched the edges and bend it like this, and the measured learning rates before and after the distortion. And we also explored the learning rates before and after the shape was differently distorted. To achieve this, participants underwent an experiment where they adapted to different visual motor rotation for forward right and forward left targets. And in the inward learning group, participants were given clockwise visual motor rotation for the right target and counterclockwise visual motor rotation for the left target, which caused the movement to shift inward. On the other hand, the outward learning group ran the opposite direction of the visual motor rotation, causing the movement to shift outward. We then examined the visual motor mapping before and after this learning. Initially, all participants had a straight visual motor mapping, but after the learning processes, inward learning group showed a flatter mapping, visual motor mapping, while the outward learning group showed a steeper visual motor mapping. Using this method, we were able to manipulate the shape of the visual motor mapping. So how does this distortion in the visual motor mapping affect motor learning? In the inward learning group, the range of movement is shrunk, while in the outward learning group, the range of movement is enlarged. Based on this, I hypothesize that the motor learning rate becomes smaller in the inward learning group and larger in the outward learning group. We measured adaptive responses in the central target because the movement directions are consistent across groups and before and after learning. Okay, so we examined single trial motor learning rates. We presented a target in the central direction, applied a visual motor rotation, and then measured how much the movement changed on the next trial. Both groups shows about 7 degrees adjustment in response to 30 degrees visual motor rotation here, visual error here, before distorting the visual motor mapping. And interestingly, in the inward learning group, the amount of learning decreased, while in the outward learning group, the amount of learning increased. So these results demonstrate that adaptive response changes according to the distorted visual motor mapping and suggesting that motor learning changes the subsequent learning behavior. So at this time in 2016, I was unable to provide solid computational explanation. So it was qualitative prediction like shrink and enlarge. We then already realized that the changes in motor learning rate cannot be explained by the computation models that have been proposed so far. For example, in structural learning theory, it is suggested that repeated error correction pairs helps acquisition of effective motor corrections, resulting in an increased learning rate. However, both the inward learning group and outward learning group in our study experienced the same error correction pairs, although the error directions were assigned to the different targets. So this idea makes structural learning theory impossible to explain our results. In addition, environmental consistency theory shows that the learning rate increased when consistent errors are presented, while it decreased when random errors are presented. However, again, since both the inward and outward learning groups receive errors at the same frequency, it cannot explain the difference in learning rate changes. Similarly, there are ideas suggesting that if we can predict what kind of error will occur, the motor learning rate will increase. However, for the same reason, the predictability of errors does not differ between groups, so it cannot explain the difference in the change in learning rates. Recently, the coin model has been proposed where metaparameters inferred the context for motor learning. This model can just explain the above cases, but again, it cannot explain my findings. Another issue of these models is that they modeled motor learning in a single target condition. They have not been able to examine how motor learning for one target affects learning for the other target, such as in my experiment. Together, the existing computational models cannot explain my results, and a new model is required to account for our findings. In contrast, the motor primitive framework can explain the generalization across targets. So I considered whether this model could be extended and will explain our results. I start to explain a motor primitive framework in the detail here. In particular, the framework would yield a motor learning rate, this one, for modeling for each movement direction that is proportional to the number of units activated for that direction. For example, if you intended to make a movement toward minus 30 degrees visual target, not all motor motor units, but some units are activated. And then motor commands would be produced by a weighted sum of the motor unit activities. If error is produced by an external perturbation, the weights corresponding to those unit activity, those motor units are largely updated. The change in learning rate is modulated by the amount of motor unit activity that is associated with the error. To summarize, in the motor primitive framework, the amount of motor unit activity determines learning rate. The motor unit activity is mainly approximated by a Gaussian function, which is defined by two parameters, the center and the width of the Gaussian. However, in traditional models, these values are assumed to remain constant regardless of learning, which means that this model cannot replicate my result. But is it biologically possible for these parameters to remain unchanged during learning, as assumed in the model? After reviewing multiple papers, I have found the answer is no. The neurons in M1 are thought to have specific representations of movements. Many studies examined horizontal arm reaching movements during neural recordings in monkeys and found that neurons in M1 display broadly tuned cosine-like patterns of activation across different movement directions. The activities of these representative neurons from a study by Jogopoulos and colleagues in 1982 here was highest when the monkey reached in this 135 degrees direction, but smallest when the monkey reached in the 315 degrees direction. If you look at the pattern activity across different reach directions, we can see clear direction-dependent tuning, and the direction where the highest activity takes place is generally called the preferred direction. Interestingly, motor learning is known to change this neural representation. In particular, after adapting to dynamic force field perturbation or kinematic visual motor perturbation, the PD is systematically rotated. For example, the preferred direction of this example neuron rotated clockwise from around 160 degrees to about 120 degrees after clockwise force field learning. The PD rotation, preferred direction rotation, is thought to reflect changes in motor action. If clockwise force field perturbation is applied, reaching toward the frontal target requires you to generate additional leftward directed motor command. So neurons that produce leftward force should be more active during forward reaching movement. That's why the direction of peak activity, that is the preferred direction, is rotated in the clockwise direction after clockwise force field learning. The PD rotation appears to be a general feature in motor cortical areas such as M1 premotor cortex and supplemental motor cortex. The key idea behind my project is that the process of PD rotation should systematically influence the subsequent motor learning. We go through a sketch that lays out the mechanisms for this. To start, this figure shows neuronal activity across movement direction, represented by local tuning curves. Each neural unit plotted has different PDs, and PDs have been found to be mostly uniformly distributed across each directions, as pictured. However, consistent with the fact that learning of force fields and visual motor perturbation is local to the trained target direction. The PD rotations have also been found to be local. And interestingly, the locality of PD rotation would lead to an increased density in the PD distribution in the area to which the local rotation occurs here. And at the same time, an increased sparsity in the PD distribution in the area from which the local rotation occurs here. So critically, these changes in PD density would systematically alter the number of these units that are activated for movements in different reach directions. In particular, there would be a greater number of these neurons activated for reach direction with increased PD density and a smaller number of neurons activated for reach directions with decreased PD density. Therefore, if these units themselves or downstream consequences of their activity were involved in subsequent motor learning, and then learning ability should be enhanced for target directions with increased PD density, and it should be reduced for target directions with decreased PD density. Okay, so I start building more specific prediction to be validated with a behavior experiment. Consider simple reaching movement. We can accurately perform reaching movement in any direction since we have an accurate visual motor mapping that transforms a visual target location in any direction into a set of motor commands that will reach the target. The ability to move in any direction corresponds to the existence of neurons with PDs distributed across all movement directions. Thus, PDs cover all locations in the visual motor mapping, and the PDs are thought to be fairly uniformly distributed at the baseline, like this. However, motor learning is known to distort the visual motor mapping. VMR, visual motor rotation, is a directional perturbation where the cursor motion is skewed from hand motion. And to correct the error, hand motion must be skewed in the opposite direction. Importantly, the motor learning effects are locally generalized and thus deform the visual motor mapping like this. This example assumes Gaussian-like generalization for 80% motor learning over 30 degrees VMR with 30 degrees width. So based on neurophysiologic findings, we know that the preferred target direction of neurons in motor cortical areas are rotated due to motor learning. And these sets consistently code not target, but movement directions. Critically, this corresponds to a horizontal shift on this visual motor mapping brought for cells local to trained target direction. And this horizontal shift changes the density of the preferred target direction distribution with an increase in density in the negative target direction here to which the PD rotation occurs, but a decrease in density in the positive target direction here away from which the PD rotation occurs. Therefore, VMR training transforms the isotropic distribution of PDs at the baseline into an anisotropic distribution following training. Note that analytically, it is the gradient of visual motor mapping that determines relative changes of PD density as a global shift in the overall mapping that would maintain its slope with preserve uniform PD density. So specifically, we can predict that after 30 degrees VMR training, the PD distribution will be 50% denser in the negative target direction and 50% less dense in the positive target direction for an expected adaptation level of 80%. And we found we would correspondingly predict a pattern of learning rate increase and decrease of up to 50% each. That matches the biphasic patterns that display in PD density changes. Okay, so we designed a behavior experiment to determine whether the direction-dependent modulation of motor learning rates predicted by PD rotation-based density changes is present in human motor learning. So 22 participants performed simple point-to-point reaching movement to train on a 30 degrees VMR in a single target direction here, 0 degrees target direction. Half of participants were trained on 30 degrees clockwise VMR and half on 30 degrees counterclockwise VMR. And the BMR was gradually introduced during the training block at the rate of just 0.25 degrees per trial. And then after this 120 trial lamp maintained at 30 degrees for 200 trials here. After the training period, there was longer 950 trial block where we interspersed measurements of the single trial learning rate and 30 degrees BMR top-up trial to ensure maintenance of the trained adaptation. And this mirrored the baseline block that was identical, except that the corresponding top-up trials there displayed no rotation. Participants successfully adapted to the perturbation, and as consistent with previous studies, the amount of learning is about 80%. The clockwise training data was embodied in this figure and as follows. In both the pre-training and post-training block, we measured single trial learning rate using a pair of perturbation and probe trial. In the perturbation trial, we introduced cursor clamping perturbation, wherein the cursor path was constrained to the path that was directed either plus or minus 7.5 degrees away from the test target. We then measured single trial learning by determining the change in the hand motion from before to after the 7.5 degrees cursor clamping perturbation. We introduced 15 times each for 10 different target directions in a pseudo-random order for each block, pre-training and post-training block. By investigating single trial learning in this way, we can accurately examine the effects of motor unit activity. In the motor primitive framework, the weights are updated based on errors, E. And the influence of these updates on the next trial behavior, xi plus 1, can be calculated by multiplying this by the motor unit activity denoted as A from the back. When we rearrange this equation, we arrive at the final form at the bottom according to the second term square motor unit activity predicts the learning rate. However, the first term here contains a non-motor primitive factor. So we need to eliminate these unrelated factors to isolate the effect of motor unit activity on learning. To address this issue, we can resolve it by using the cursor clamping perturbation method, which keeps the error magnitude constant. In this method, we applied a fixed error of 7.5 degrees denoted as E plus and measured the adaptive responses X plus. Similarly, we applied a fixed error of minus 7.5 degrees denoted as E minus and measured the adaptive responses as X minus. By taking the difference between these two responses, X plus minus X minus, we can cancel out the non-motor primitive factor, such as AX, leaving only the motor primitive factor to be examined. So this approach allows us to isolate and accurately assess the influence motor unit activity on the learning process, and providing cleaner insight into the relationship between motor primitive dynamics and adaptive responses. Okay, so now let's look at the results. So in the baseline condition, participants are able to move straight toward any target. And this is represented by the diagonal line in the figure modeled as y equals x. After running a 30 degrees visual motor rotation in the training block, we observed generalization of motor learning effects centered around the 0 degrees learning direction. These generalization patterns are consistent with previous studies, and we fit them with a Gaussian function. Based on this fitted function, we estimated the unit activity and predicted changes in motor learning rate as previously explained. We also observed a biphasic pattern in our dataset with a peak magnitude of approximately 40%. Okay, so note that the model assumes that the preferred directions are uniformly distributed at baseline. And I would like to ask the previous question once again here. Is this strong assumption biologically possible? In fact, previous research has investigated the distribution of preferred direction in the motor cortex. And interestingly, it has been shown that distribution is not uniform. These studies report that there are a large number of neurons whose peak activity occurs when moving the right hand in the left forward or right backward direction. This is thought to be determined by the structure and physics of an arm. So what predictions can we make if the PDs follow such a skewed distribution? To investigate this, I manually counted the number of neurons from figures in these studies, and based on that, I created a new distribution with the same degree of skewness. After counting, I found that the number of neurons in this diagonal direction was 2.7 times higher than the number in the opposite diagonal direction. Using this as a basis, I created an initial distribution that reflects this skew. This is shown as a polar histogram, where the distribution faithfully reflects the data from these previous studies, with the number of neurons peaking in the left forward and right backward direction. When simulating with distribution, we must consider the effect of PD rotation separately for clockwise and counterclockwise visual motor rotation or training, as they produce asymmetric effects. Let's examine these cases in parallel. During each training, the visual motor mapping shifts in different directions, causing the PDs to rotate accordingly. And as a result of these shifts, the original distribution changes. In the case of clockwise training group, the skewness becomes more pronounced, while in counterclockwise training, the skewness is somewhat reduced. The density distribution shows that in clockwise training, the peak becomes higher in clockwise training group case, and in counterclockwise training case, it becomes lower. So these differences in distribution predict distinct changes in motor learning rates. For instance, in the negative target direction, the red increase is larger than the blue decrease because the difference between the red and green is larger than between the blue and green, indicating a more significant effect for the red distribution. In the regions where the densities overlap here, the changes are very small, but in the positive target direction, the effect reversed. So this suggests that the baseline distributions influence the pattern of the subsequent motor learning rate. To combine the clockwise and the counterclockwise training, we inverted x-axis with respect to the training direction and computed the average as shown in the figure. The average is represented by the black line. As you can see, compared to the isotropic case, the pattern is slightly skewed, even though a biphasic pattern is still observed. So this indicates that the initial PD distribution plays a crucial role in shaping the motor learning response. So far, we have derived two predictions. The first one assumes a uniform distribution at baseline, leading to a symmetric prediction. The second one assumes a skewed baseline distribution, resulting in different predictions depending on the target direction. We investigated whether actual data shows biphasic shape, and if so, investigated which one is a better prediction. So here's the data. First, it's important to note that we observed biphasic pattern from the data as well. Unfortunately, the single-train learning measurements showed considerable variability, making it a bit difficult to interpret. However, when we compare the correlation with both predictions, we found that incorporating the biologically plausible skew distribution led to a slightly higher correlation coefficient, indicating it was a better prediction. For further analysis, we computed the means at region 1 with higher values, minus 15, minus 30, minus 60 degrees target direction, and at region 2 with smaller values, 50, 30, and 60 degrees. The predictions for the isotropic and anisotropic cases were represented by solid and dashed lines, respectively, and we found that the actual data more closely resembles the anisotropic case, especially in the blue case. These results suggest that PD rotation, perhaps from biologically plausible baseline distribution, determines the subsequent model. Right. So it's an interesting feature that the shape of the visual model mapping is related to the motor learning. In the negative target direction, the slope is steeper compared to the original mapping, while in the positive target direction, the slope is flatter. This slope corresponds closely to the distribution of PDs, suggesting that the slope of the visual model mapping is indeed related to the model learning rate. Importantly, this is completely different from the gradient descent algorithm commonly used in machine learning. In gradient descent algorithm, the cost function is defined as the squared error. In this case, the error is defined as the difference between the movement direction, target direction, and the perturbation. To minimize the cost function, learning progresses by calculating the partial derivatives of L with respect to M and adjusting the movement accordingly. And interestingly, the learning rate eventually becomes proportional to the partial derivative of V with respect to M, especially when perturbation is small enough. Thus, the human sensorimotor adaptation discovered in our experiment is essentially the inverse of gradient descent algorithm. So what's this? In fact, it aligns with another optimization algorithm, namely the Newton's method. With this figure, we explain how Newton's method works. The x-axis represents the difference between the movement and the target directions, and the y-axis represents the square error. The point we want to find x star is at the minimum of this curve. That is the minimum of the squared error. At first, because the participants do not know the presence of the perturbation, they move straight towards target here. So squared error is at the point of the curve represented by this red point. So what Newton's method does is calculate the tangent line at this point, and this line tells us how much motor learning happens. And Newton's method determines the amount of motor corrections delta x, where the line crosses x-axis. So if the error hasn't been fully corrected yet, Newton's method recalculates the error and uses the new tangent line to determine the amount of motor correction on the next. The slope of the tangent line is essentially the squared error over the delta x. So the amount of motor learning is proportional to the squared error over its derivatives. Because the derivative is a partial, this derivative is partial derivatives of v with respect to m, the amount of motor correction delta x is proportional to the partial derivatives of m with respect to v. Thus, prediction of Newton's method matches our result. This suggests that human motor adaptation is based on Newton's method rather than gradient descent algorithm. One might wonder if this approach could be suboptimal. However, in the context of motor adaptation, it is actually quite efficient. Newton's method works particularly well when we are close to zero-error solution. So in this region, it can quickly refine the solution and minimize error without excessive adjustment. If the gradient is steep around that zero-error solution, taking too large a step could cause the algorithm to miss the optimal point and overshooting it. So small step is necessary to control the risk. To finely tune the solution to ensure that we reach the exact target, that is a zero error, smaller steps are crucial, especially when we are near the optimal point, like in human model adaptation. Interestingly, in machine learning, training is typically stopped before the model has fully converged to the zero-error solution. This early stopping strategy helps prevent overfitting and improve generalizability. In contrast to machine learning, model adaptation often happens near the zero-error solution. This is where Newton's method offers an advantage, as it is more effective when operating in such a neighborhood, making the more suitable model for model adaptation. All right. So in conclusion, we first theorized that local model learning would result in a specific pattern of anisotropic changes of PD density based on distortions in the visual model mapping. We then hypothesized that these changes in the PD distribution would predict systematic direction-dependent changes in the rate of single-trial model learning. And we found that these predictions were borne out by experimental measurements of single-trial learning. These PD density-based predictions were approximated by Newton's method rather than gradient descent algorithm used by modern machine learning. Therefore, we show that PD rotations that underlie model learning can result in dramatic changes in the ability of the model system to learn from subsequent model learning or model learning experience. Okay, I appreciate Professor Daichi Nozaki, Professor Ken Takayama, and Professor Morris Smith, and the students and postdocs gave helpful advices and comments. I also thank the foundation giving me an opportunity to do this work. Thank you very much.
We have time for questions.
Everyone, thank you very much. It was a really great talk. Beautiful diagrams that made things really easy to follow. So thank you. Had a couple of questions. So the main thing is I didn't quite understand the conceptual link between why you expect an increase in motor learning rate when you have an increase in preferred direction density around a particular direction. So I understand that the units that are involved in representing that direction will be closer together, but why does that necessarily, or why would that intuitively lead to a change in sensitivity or a change in learning rate?
I see. Thank you very much for your question. So you may understand why the PD rotation occurs in horizontal axis, right? But
Yep.
your question, yes. But your question is why this PD rotation could influence the motor learning rate.
Yep.
Yeah, I see that problem actually. Yeah, this is my hypothesis and still be one assumption. You know, we have our hypothesis is that this PD rotation or PD in the motor cortex should influence the motor learning. So these changes of neural representation also impact on the motor learning rate and subsequent motor learning. So that's we didn't measure neurophysiology stuff, so we don't know. But this is our hypothesis.
Yeah, I mean, I guess it makes sense in some respect because you have more units that are active when that error is going to be received, and so potentially they might be changing more, but it's not exactly clear what is the link between more units around a particular area of space and how much those units might then result in an adaptive process of learning. So yeah, it'd be nice to think about that and see if you could work out, what kind of, physiological mechanism that might speak to.
Maybe
Thank you.
sorry. Just following on that, I'm not very familiar with the neurophysiology work, but I think like I know you talk about, single trial learning, but I think that there could be evidence on the longer time scale that correlate the changes in the preferred direction with things that happen on a slightly longer time scale. So when you learn say one rotation or one perturbation, one force field, and then you have some time delay in a second. I think Elon Badia might have some of that work. I think. Please correct me if I'm wrong.
Yeah, I agree that there are probably many time constants. There are many time constants. For example, one cell changes rapidly, but the other cell changes very gradually. So I'm not sure what how this cell, influence model learning. But still, in this experiment, of course, we did just two hours experiments and so on. So it should be a very rapid one. This result should indicate that rapid one influence model learning rate.
Can I make a observation? It's not a question. So Takuji, it might relate to what Tim was asking. So you're probably familiar with attentional warping, right? So in attentional warping, if you put people in a scanner, so what's going to happen? You say, just watch this video, and certain parts of the brain are going to respond to cars or people or objects or things like that. So that's what the baseline state is. But now you tell people, oh, watch that same video, but pay attention to cars only. Neurons that were responding to people are going to respond to cars now. So these neurons are not just representing cars or people. They can represent different things depending on what the task is. So that kind of reminds a little bit of that. And of course, if you say, well, detect cars in the environment now, they're going to detect more. So to me, that's translating to more adaptation as well. I don't know if the analogy makes sense, but
thank you very much. That's an interesting point.
Yeah, it's just something to consider. I told you there was no question there, but I think it really is related to what Tim is asking as well.
Yeah, thank you. I will consider more about it later. But in my tuition now, in our experiment, they're very, how do you say, the participant attention level is kind of low, and there are not a lot of things to attain, right, on the screen or behavior experiment. So, the attentional things shouldn't affect big.
Oh, sorry, I'm just gonna rephrase that. It's not about attention itself. It's just that the neurons. So some neurons are tuned to certain directions, but it doesn't mean that's a constant thing, as you're showing. They can be tuned to other directions as well. So that's the analogy that I'm making between attentional warping in your work. So to me, it's very similar. So to me, it's biologically plausible given what I have seen in attentional warping.
That's interesting one. It might be interesting if the attentional things and learning rate, like I proposed, is associated, like changing, simultaneously. Thank you.
Thanks, Takuji. Thanks for the great talk. Like, this is really interesting. I have a few questions. So I guess it mainly surrounds the type of errors that drive this PD change. So in your initial training, like you introduce visual motor rotation.
Mhm.
And then in the testing phase, you introduce a 7.5 degrees clamp, which we
Right.
think is a different kind of error, right? Like in the VMR, there's a
Yeah.
combination of task
Mm.
error and prediction error, whereas in the clamp, we think that is only sensory prediction error. So in that sense, what do you think is what kind of error do you think is driving your result? And could you sort of reinterpret your results within that task error, sensory prediction error kind of framework?
Mm. Thank you for the question. Mm.
Yeah. So it's a different errors in the two different phases.
Yeah. Mm. That's a good point. Yeah, recently many studies want to dissociate task error and sensory prediction error. So we have to think about it more. But in this
Yeah.
study, I just combined the idea of kinematic perturbation for both cursor clamping perturbation and visual motor rotation perturbation. So that's a great point. I have to think about it more. Thank you. Sorry, I have no specific answer yet.
Oh, good. Yeah. Like it would be cool if you can do like a like a prediction error specific one and a task error specific one, and then you see that all the preferred direction changes is driven by one type of error, but there's still this link as to why that change in PD would change adaptation as well.
I see. That's interesting.
Another one, if that's okay. But since this slide is up, I actually didn't quite understand the way that you use the perturbation trial pairs versus the probe trial pairs differently. Can you explain that to me?
So say again.
I didn't quite understand how you've got two pairs with a clamp and then a free movement, and then you've got a zero error clamp and then another movement. I didn't see the difference between the probe trial and perturbation trial pairs into how you were assessing single trial learning.
Okay.
So
So
yeah.
the training always occurs at central target, 0 degrees target, but we have to check the motor learning rate in different target direction, right? So I inserted the pair of perturbation and probe trials for this target, for this test target during the training, right? And the logic is here, right?
Oh, sorry.
So
No, it's okay. I get it now. I was confused. I thought that there was two trials in the perturbation, but really you're just showing
There's one.
the hand motion.
Yep.
So it's just one trial and then there's a second trial. Gotcha. I thought there was 4 trials there, but there's only 2 trials there. So that makes sense.
sorry, this is
Yeah.
hand motion. Yeah.
Yeah, no, it's fine. Gotcha.
Yeah, it's a 7.5 and then a 0.
Yeah. No, that's fine. Thank you. I guess we've got one more if that's okay. But in terms of the Newtonian method of sort of reducing errors, I just wanted to know how the subject or the participant has access to that function. How do they have access to the slope, and how do they know where the error versus like the squared error versus error function should converge? So what distribution of information do they have that allows them to make that prediction?
Are you talking about kind of here?
No, a bit further. With Newton's method, when you did the So trying to predict right at the end, I think when you did Newton's method of convergence or learning rate changes rather than the gradient descent method.
That's one.
So here, yeah. So if you go back to the graph, so obviously, yeah, it makes sense. How does the subject know the function? So if they only got one error, then they don't know where the squared error versus movement direction changes are. So obviously, they're going to have a big error, but then they have to get exposed to many errors to understand that function so that they can predict the gradient. So
In my opinion, participants or brain know this function because they have a visual model mapping. They
right.
know what they can. If you have a accurate visual model mapping, they can imagine what happens if the error. If the error, if the what happens if the movement is slightly rightward or slightly leftward, then they can easily, calculate the slope.
Yeah, I guess because it's an inherent sort of physical property, so the brain gets exposed to that over time and recognizes that this is okay. So it's just kind of conceptualizing that if it's a big error, they should, yeah. I mean,
I'm guessing, I don't know if you have tried this yet. Could you like the shape of this slope, the shape of this U might correlate with the density of your preferred direction, and that would provide like a explanation of the sensitivity of your change in adaptation. So if the slope is steep, right, people would change. I don't know, what would you predict? People would change less in a way if it's very, very steep U.
Yeah. Yeah, again, I have to mention that the Newton's method cannot explain all our motor learning behavior, right? For example, learning rate often decrease if the learning is getting very large, for example, 30 degrees, 45 degrees, 90 degrees. But this idea that if the error increased in this direction, then the amount of correction is, getting bigger. So this cannot explain, the model learning for all model learning features in human. So I agree that there is a limitation.
Yeah, I know. I'm just suggesting that maybe if you say for a fixed amount of error, and you change the shape of this U according to your preferred direction width, would that then better explain your data?
I see.
But there's still no sort of physical reason for it. But it's just a model kind of play. Yeah.
I don't know, actually.
Yeah, just a suggestion.
Thank you. It's very interesting if you control or manipulate the width of the, motor primitive activity or, neural tuning. But to my, I'm not sure how we can do. We can, manipulate that.
Now, I think Welber's suggestion might relate to the tuning width thing, right? So if you're associating things together and the same units can represent different categories, you might say that for directions, you don't just have a shift in the preferred directions, but you have a broadening, a width, a widening of the function of the tuning function. So that would conceptually follow, I guess, from the type of thing Welber was talking about. So it'd be interesting to, see if there's evidence for that, and also if any of that extra parameter helps with the models.
Thank you. That's interesting.
I agree. Yeah. Well, one interesting question that you and I probably might find interesting is like, is it the motor cortex doing this transformation?
True, yeah.
What do you mean? So do you think it's also it comes downstream?
Yeah, I don't know. It could well be that's coming from elsewhere, and just motor cortex might be reflecting that, and informing spinal cord.
I guess we have to look at those old experiments and see where else they recorded, and did they find different directions for, say, those downstream areas?
Yeah,
Most of those studies, they don't know where the neurons they're recording from were projecting, so they could have been projecting anywhere. So certainly possible that it could be upstream or downstream of the cortex.
Yeah.
And potentially distributed at multiple places.
Yeah.
I think, yeah, I can only answer that like in, say, rat studies where they do the retrograde tracing and they,
Yeah, I don't know. What was crossing my mind is like if that decoding, EEG decoding of direction could inform us anything. So if we can see which part of the brain have allowance to predict the direction or how much adaptation there is. I don't know. Just guessing. This might only make sense to me and Tim because we have discussed that in the past, so I apologize if it makes no sense whatsoever to anyone else.
Thank you so much for a really, really excellent presentation, Takuji. Do we have
Thank you very much.
do we have any further questions from the audience? So yeah, with that, I'd like to thank Takuji for an excellent presentation. I'll make this recording available on the channel again. And as always, if you have any suggestions for speakers, please let me know. We'll keep working on trying to curate a list of presentations that are topical and of broad interest to our audience here. Please email me if you have any suggestions. Thank you so much.
Thank you.
Thank you so much, Takuji. It was really interesting talk. Really appreciate it.
Yeah, really cool.
Thank you so much.
Thank you. Thanks.
Bye, everyone.
Right. Leanne, you want to have a quick chat after?
Oh, hang on. Yep.
Or perhaps
Yeah.
stop recording.
I'll stop recording. We'll just, Takuji, we're just gonna stop recording.